Today we are going to discuss about the C2h point group. The symmetry operations of C2h point group are E, C2, I and sigma h. E is identity, is doing nothing, it is present in every point group. Next we see the example of hydrogen peroxide, which is planar and trans with respect to the OH bonds. And the molecular plane is perpendicular to the C2 axis. The C2 axis passes through the OO single bond and it is perpendicular to the molecular plane. We will try to understand the C2 rotation. We have differently colored the two hydrogen atoms. This is colored yellow, the other hydrogen atom is colored brown. C2 is the rotation of 180 degrees, and when you rotate it through 180 degrees, the hydrogen atoms are interchanged. This brown hydrogen atom comes here, the yellow hydrogen atom comes there, and upon another 180 degree rotation, the original positions are restored. Upon 360 degree rotation, the same appearance is repeated twice, and so the axis is C2. Next we come to the center of symmetry. From an imaginary center, if you draw a line, we get a hydrogen. If you draw another line in the opposite direction through the same distance, once again you find the hydrogen. So center of symmetry is present and inversion will occur. Next we come to the plane which is perpendicular to the principal axis. There is only axis is C2 axis, and so there is a principal axis. And the plane that is perpendicular to the principal axis is the horizontal plane of symmetry, sigma h. It is like if the plane is a white sheet of paper, and if the principal axis is like a pencil, the pencil is placed vertically over the plane, then you call it as horizontal plane of symmetry. The plane of symmetry cuts through all the atoms present here, the two hydrogens and the two oxygen atoms. One half of each atom is above the plane, the other half is below the plane, and this is the horizontal plane of symmetry. The four operations E, C2, I and sigma h constitute the C2h point group, and so the transplanar H2O2 is an example for C2h point group. Next we come to this example, trans 1,2-dichloroethylene. The C2 axis passes through the carbon-carbon double bond and it is perpendicular to the molecular plane. And we will try to understand the C2 rotation like this. We will color the chlorine atoms differently. This is yellow colored and this is brown colored. Upon 180 degree rotation about the C2 axis, the yellow Cl will come here, the brown Cl will come there, and the positions are interchanged. Upon another 180 degree rotation, the original structure is restored, and upon 360 degree rotation, the same appearance is repeated twice, and so it is a C2 axis. Next we come to center of symmetry. From the imaginary center here, if you draw an arrow, in one direction you will get hydrogen atom. If you draw another arrow of same distance in the opposite direction, you get hydrogen atom again. Similarly, if you draw an arrow from the imaginary center, in one direction you get chlorine atom, and in the other direction, if you draw an arrow of equal distance in the opposite direction, you will get the chlorine atom again, and so center of symmetry is present and inversion can occur. Next we come to the plane which is perpendicular to the principal axis. This plane cuts through all the atoms, that is the two carbon atoms, two chlorine atoms and the two hydrogen atoms. One half of each of these atoms is above the plane and the other half is below the plane, and this is the sigma h, the horizontal plane of symmetry. Next we come to this example. This is the example of fumaric acid. The two carboxylic acid groups are trans to each other. The C2 axis passes through the C double bond C, and it is perpendicular to the molecular plane, and the C2 axis is the only axis, and so this is the principal axis. In this we have colored the two carboxylic acid groups differently. Upon 180-degree rotation, the two carboxylic acid groups are interchanged, and upon another 180-degree rotation, the same positions are restored. The same appearance is repeated twice, and so it is a C2 axis. Next we come to center of symmetry. This is the imaginary center from which we draw a line in one direction. We'll get hydrogen atom. If we draw a line of equal distance in the opposite direction, we'll get hydrogen atom once again. Similarly, if you draw a line in one direction, we'll get a carboxylic acid group. If you draw a line in opposite direction, we'll get the carboxylic acid group once again. And so this is the center of symmetry. Next we come to a plane which is perpendicular to the principal axis, namely C2 axis. This is a horizontal plane of symmetry which cuts through all the atoms of the molecule. One half of all these atoms is above the plane, the other half is below this plane, and this is a sigma h. These four operations E, C2, I and sigma h belong to C2h point group, and so fumaric acid belongs to C2h point group. Next we see N2F2. The two NF bonds are trans to each other. The C2 axis passes through the N double bond N, and it is perpendicular to the molecular plane. And we have colored the two fluorine atoms differently. This is brown and this is yellow. Upon 180-degree rotation, that is the C2 rotation, the brown will come here, the yellow will go there. And upon another 180-degree rotation, the yellow will come here, the brown will go there, and so the original structure is restored. The same appearance is repeated twice during the complete 360-degree rotation, and so it is the C2 axis. Next we come to center of symmetry. This is the imaginary center. If we draw a line in one direction, we get fluorine atom. If we draw a line in opposite direction, we get the fluorine atom once again, and so the center of symmetry is present. Next we come to this plane of symmetry which is perpendicular to the principal axis, and so it is a sigma h plane. It is a horizontal plane of symmetry. It cuts through the two fluorine atoms, the two nitrogen atoms. That means one half of each of these atoms is above the plane, the other half is below the plane, and this is the sigma h plane. Next we come to trans 2-butene. We find a carbon-carbon double bond here. Me is methyl group, and the C2 axis passes through the C double bond C, and it is perpendicular to the molecular plane. We have colored the two methyl groups differently. This is yellow, this is brown, and when you make an 180-degree rotation, the two methyl groups are interchanged. The two hydrogen atoms will also be interchanged, and this brown comes here, this yellow goes there, and upon another 180-degree rotation, the same original structure is repeated. This is the C2 axis. Next is the center of symmetry. If we draw a line from the imaginary center here, you get hydrogen atom. If we draw another line in the opposite direction, you get hydrogen once again. If you draw a line in one direction, you get methyl, and if you draw another line, you get methyl again in the opposite direction, and so center of symmetry is present. Next we come to the horizontal plane of symmetry. This plane is perpendicular to the principal axis, C2 axis, and so it is sigma H plane. It cuts through all the atoms here. We consider methyl as a single group here, and one half of each of this is above the plane and the other half is below the plane. Consider methyl as a single entity. Next we come to this molecule. This contains two double bonds. This is 1,3-butadiene and this is trans 1,3-butadiene. The C2 axis passes through the C single bond and it is perpendicular to the molecular plane. We have colored the two hydrogen atoms differently. This has brown and this has yellow, and upon 180-degree rotation the brown will come here, the yellow will go there. Similarly, these two methylene carbons will also get interchanged, and upon another 180-degree rotation the original structure is restored and the same appearance is repeated twice, and so it is the C2 axis. Next we come to the center symmetry. This is the imaginary center. If we draw a line in one direction, you get hydrogen atom. If we draw a line in opposite direction, you get hydrogen atom again. If we draw in one direction, you find the CH2 group, and in the opposite direction, if you draw a line of the same distance, once again you find the CH2 group, and so center of symmetry I is present. Next we come to this. This plane is perpendicular to the principal axis C2, and this plane cuts through all these atoms and groups. CH2 group is considered as single entity, and anyway this CH2, all the hydrogens will remain in the plane because this carbon is sp2, the shape being trigonal planar. All of them will remain in the same plane itself. One half of each of this atom is above the plane and the other half is below the plane. This is the sigma H plane. Next we come to 1,5-dichloronaphthalene. The C2 axis passes through the fused bond, the bond that fuses the two rings. The C2 axis passes through the carbon-carbon fused bond at the ring junction, the junction of the two rings, and it is perpendicular to the molecular plane. And if you look at this, the two chlorine atoms are colored differently. Upon 180-degree rotation, the two chlorine atoms are interchanged. Yellow comes here, the brown comes here. Upon another 180-degree rotation, the same structure is repeated, and so it is a C2 axis. This is the imaginary center. If you draw a line in one direction, you get chlorine atom. If you draw a line in another direction, you get a chlorine atom again, and so center of symmetry I is present. This plane is perpendicular to the principal axis, and so it is a horizontal plane of symmetry. It cuts through all the atoms, all the carbon atoms, all the hydrogen atoms, and all the chlorine atoms. One half of each atom is above the plane and the other half is below the plane, and this is the sigma H plane, the horizontal plane of symmetry. If we summarize, the transplanar hydrogen peroxide, trans 1,2-dichloroethylene, fumaric acid, trans N2F2, trans 2-butene, trans 1,3-butadiene, 1,5-dichloronaphthalene, all of them contain the symmetry operations as E, C2, I and sigma H. So all of them belong to C2H point group. Thank you.